Hi all, welcome to Go Classes. So let's start this session. In this session, we are going to discuss GOAT DPP series. Today's DPP is Digital Logic subject and the topic is Boolean Algebra and K-map. Okay, so let's start the discussion session. So did you attempt all these questions? There are 5 questions. All these questions are taken from GATE Biomedical previous year questions. So did you attempt? Always attempt the questions by yourself before joining the video solution. Okay, so we will do the complete analysis of all the questions in this session. Is the audio video clear? Audio video everything is fine, everything is clear. Lakshman, I will cover it, don't worry. So right now let's focus on this session. Let's solve all these 5 questions from GATE Biomedical PYQs with complete analysis. So let me tell you about it, that we have started on Go Classes YouTube channel. For GATE CS, we have started GOAT DPP series, basically Go Classes YouTube DPP series. So you can see this series we have started. And in short, let's call it, Go YT series. So let's call it, GOAT. Okay, so GOAT DPP series. And the playlist link for the GOAT DPP series, the complete playlist link, you can find the link in the description, also in the pinned comment. All the questions will be taken from the standard resources to ensure that you practice top quality questions. You can see in this session, we will solve 5 questions from Digital Logic, Boolean Algebra, and K-map. All these questions are taken from GATE BM PYQs. Okay, so let's start this session now. Let's solve GATE Biomedical 2026 question. This question is based on K-map. The question is saying, this question 49. The figure below shows the Carnot map, K-map, for a truth table with 4 variables A, B, C, D. Which of the following expression represents the minimum sum of product expression? So the question is asking for minimum SOP, minimum sum of product expression. The empty cells in the K-map, they are 0. We already know that in the K-map, the empty cells, they are basically 0. Okay, now these options are given to us, and let's find what is the minimum sum of product expression. From the K-map, how to find minimum SOP? Very simple. To find the minimum SOP, you will cover all the 1 cells with minimum number of cubes and every cube as large as possible. Yes or no? Very simple. So remember, just cover all the 1 cells with minimum number of cubes, every cube as large as possible, and you will get the minimum SOP expression. Here, before we find the cubes, let me label the areas in this K-map. You can see on the column we have CD, and on the row we have AB variable 0001 1110 0001 1110. So this is a standard K-map. Now in this K-map, let's label the areas. So you can see on the column we have CD variable. You can see that the variable C, that is 1 in these 2 columns. So this is the area. This is the area for C. So this will be the area for C bar, and this will be the area. These last 2 columns will be area for C. And you can see in the middle 2 columns, the variable D is 1. So that is the area for D. You can see in the last 2 rows, the variable A is 1. Correct? You can see the variable A is 1 in the last 2 rows. So this is the area A. And in the middle 2 rows, the variable B is 1. So this is the area B. So first we label the areas in the K-map. Now let's see how to cover the 1 cells with minimum number of cubes, every cube as large as possible. You can notice one thing. Look at this one. For this one, this is a useless neighbor because here the function value is 0. Okay, this is a useless neighbor. This is a 0 cell. This is a useless neighbor. So there is only one useful neighbor, that is this. Because remember, we can fold the K-map horizontally, vertically. Correct? Okay. So if I fold the K-map horizontally, then you can easily see that these two cells, they are neighbors. Correct? They are adjacent cells because they differ in exactly 1 variable. Okay, so here you can see for this one, there is only one useful neighbor. This is that. Okay, so you can see what this one will do, what this one cell will do with the useful neighbor, it will create a cube. Okay, so you can see this cube will be created. Very simple. Now let's see. Look at this one. This one, from this one point of view, you can see this is a useless neighbor because this is a zero cell, useless neighbor, useless neighbor. There is only one useful neighbor, that is this one. Okay, so this cube also will be created. Very simple. Now let's see. Look at this one. From this one cell point of view, you can see this is a useless neighbor. You can see this is a useless neighbor, and you can see this is a useless neighbor because these are the zero cells. So these are useless neighbors. Okay, there is only one useful neighbor. So with help of that useful neighbor, we can create this cube of size 2. Okay, very simple. Now you can see that this 4 size cube we can create. Okay, because you can see, remember this one and this one, they are still remaining, we did not cover them. So what we can do, we can make this 4 size cube we can make. Okay, so now I can say that we have covered all the one cells with minimum number of cubes, every cube as large as possible. So we will get our minimum SOP expression. Now what you can do to write the minimum SOP expression, for each cube covering one cells, you write the product term. Okay, so let's write the product term for this cube. You can see this cube, this is in the area D bar, also in the area A, also in the area B, correct? Okay, yes or no? Look at this green cube. This is in the area, this is in the area A, this is in the area B, also this is in the area D bar. Okay, so AB D bar. This is the product term we will get corresponding to this cube. Now, what about this 4 size cube, this orange cube? So what is the product term for this 4 size cube? You can see this is in the area B, also in the area C. So you can see BC. This is the product term we will get for this cube of size 4. Next, you can see what is the product term we will get for this 2 size cube. This pink cube you consider. This is in the area B, this is in the area D, also this is in the area A bar. You can see this is in the area A bar, in the area B, in the area D. Okay, simple. And now you can see that this blue cube is remaining. So what is the product term corresponding to this blue cube? This is in the area C, this is in the area A, also D bar. So you can see this is in the area A, then C, then D bar. Okay, very simple. Now once we have written the product term corresponding to all the cubes which are covering one cell, so we can write the minimum SOP expression. What is the minimum SOP expression? Just do the OR of these product terms. SOP means sum of product terms, correct? So just do the OR of these product terms. So the answer we will get, that will be BC or A B D bar or A C D bar or A bar BD. Okay, so very simple. This is the minimum SOP. Now you can check which option is correct. So you can see we have BC, right? So option B, D I can eliminate because in the minimum SOP expression we have BC. Okay, so you can see option A, option C. Which of them is correct? You can see in the option C we have AC D bar. Do we have AC D bar? Yes, we have AC D bar. In the option C we have A bar BD. Yes, A bar BD. And you can see in the option C we have A B C bar D bar. That we don't have in the minimum SOP. So this is also gone, and the answer will be option A. Okay, you can check BC or A bar BD, BC or A bar BD, or you can see ACD bar. We have here ACD bar, or we have ABD bar. Okay, so very simple. So I can say that answer will be option A. Now in this question, let's find the number of prime implicants, number of EPI. Those also we can find. Let me tell you one important thing, that the GATE 2027 syllabus has been changed, right? For GATE 2027, there are some changes in the GATE CS syllabus. Now, in the digital logic, if you see, they have explicitly mentioned K-map and tabular method. Okay, so if you see the 2026 GATE 2026 CS syllabus, if you see, and for computer science, if you see the GATE 2027 syllabus, then you will notice one thing, that in the 2026 computer science syllabus, they have only written one line, one word, that is minimization. But in the GATE 2027 computer science syllabus, they have mentioned minimization, and then in the bracket they have also mentioned K-map, also tabular method, correct? Okay, now many students, they are thinking that the syllabus has changed for digital logic. The answer is no, because remember, they have just explicitly mentioned these topics which are part of minimization, Actually, this K-map we already have studied, and in this tabular method, we study prime implicant, essential prime implicant. These concepts are part of tabular method. Okay, so you might be thinking you did not study the tabular method, but when you study tabular method, you will see that you will study implicant, prime implicant, essential prime implicant. These concepts you will study in the tabular method. So I am saying that syllabus did not change for digital logic. They have just explicitly mentioned the topics. In the tabular method, we study prime implicant, essential prime implicant, implicant. Those concepts we have already studied in our Go classes lectures. K-map also we have studied. So remember, for the digital logic, the syllabus did not change. I hope you understood. Okay. So let's find the number of prime implicants and number of essential prime implicants, EPI. So you can see here, what is a PI? What is a prime implicant? From the K-map point of view, prime implicant is a cube as large as possible covering ones or don't cares. From the prime implicant point of view, we consider the don't cares as they are one. Okay, so remember, from the prime implicant point of view, the don't cares we treat them as one. You consider all the don't cares like they are ones to find the number of prime implicants. Okay, now here you can see in this K-map there is no don't care, so we don't have to worry. So from this K-map point of view, a prime implicant is a cube covering one cells which is as large as possible. So I can say maximal cube covering one cells. That is the prime implicant. Okay. So here you can see this 4 size cube. This is maximal cube covering one cells. Okay. Remember, maximal, not maximum. Okay. Here you can notice one thing, that this 2 size cube, this is also maximal. This is also maximal cube covering one cells. So this is also PI. Next, you can see that this is also PI. This is maximal cube covering one cells. So this is also a PI. Next, you can see that this is also PI. This is a maximal cube covering one cells. So remember, the definition of PI is very simple. From the K-map point of view, PI, prime implicant, it is a maximal cube covering one cells or don't cares, because here we don't have don't care, so let's not worry about it. So I can say that from this K-map point of view, prime implicant is a maximal cube covering one cells. Okay, very simple. Here you can notice that we only have 4 prime implicants. You can count 1, 2, 3, 4. Okay, total 4 prime implicants we have. So the number of prime implicants is 4. And how many of them are EPI, essential prime implicant? Essential prime implicant is a prime implicant which covers at least one cell uniquely. Okay, so what you do, you check all these one cells, you check and see these one cells are covered by how many prime implicants. You can notice, look at this one cell. This is covered only by this pink PI. So I can say this one cell is covered uniquely by this pink PI. So this pink PI has become EPI. This pink PI, this has become essential prime implicant. Next, you can see this one cell, this one cell. Okay, you can notice this one cell is covered only by this blue PI. So I can say that this one cell is covered uniquely by this blue PI. So this blue PI also has become EPI. Okay, you can notice this one cell, this is covered by 2 PI, blue and green. Now look at this one cell, this is covered uniquely by green PI. Correct. So this green PI has become EPI. And you can see, look at this one cell, this is covered uniquely by this orange PI. So this orange PI has become EPI. Very simple. You can also notice this one cell, this is actually covered by 3 PI, green, orange, pink. Okay, and here you can see this one cell is covered uniquely by the green PI. So green PI has become EPI, that we have already seen. Okay, so I have put the star mark. When I put a star mark, it simply means that this one cell is covered uniquely by a PI. Okay, what it means? It means that this one cell is covered uniquely by a prime implicant. Means only one prime implicant covers this one cell, not more than one. Okay, so that prime implicant will become essential prime implicant. So here I can say that number of EPI, that is also 4. And remember one thing, when all the EPI collectively cover all the one cells, then we will get unique minimal SOP. Here we will get unique minimal SOP. And remember, this is one-way theorem. Means if all the API collectively cover all the one cells, then we will get unique minimal SOP. But if it does not happen that all the API are covering all the one cells, then remember we may or may not get unique minimal SOP. So this is just a one-way theorem that if all the API collectively cover all the one cells, then definitely we will get unique minimal SOP. Okay, for this question we will get unique minimal SOP. That is what the question is asking. So the answer will be option A. Okay, very easy question. I hope you understood. Let's solve GATE Biomedical 2023 question. Question 28. QRS, these are Boolean variables and this symbol is for XOR operator. Select the correct options. This is a MSQ question. One or more options can be correct. Now this question is purely based on XOR. So let me tell you that on the Go Classes YouTube channel, you can find this lecture. And this lecture covers all about XOR, XNOR, the difference between XNOR gate and XNOR function. So everything is covered in here. All about XOR, XNOR is covered in this single lecture. You can see this is just a 1 hour lecture. You can watch it. And after watching this, you will feel very confident in XOR, XNOR. Okay. So on YouTube, you can search XOR, XNOR Go Classes, and this 1 hour lecture you can watch. The important point is that in this lecture, I have also covered XNOR gate and versus XNOR function. Basically, the difference between XNOR gate and XNOR function, that also I have covered. In this lecture, I have covered that XNOR function and XNOR gate, they are basically different, and the difference I have covered. Okay. Also, I have solved gate electronics 2010 question and gate electronics 2015 question in this session. And one more interesting thing, that in the gate electronics 2010 and you can see in the gate electronics 2015, two questions came which are kind of unique questions which have never come in the gate CS so far, but in the future maybe they can ask you. Okay, so that is the reason I strongly recommend you to watch this video. Here you will get to know a lot of new things. Okay, so let's solve this gate BM 2023 question. QRS are Boolean variables, and this question is related to XOR properties. Let's see option A. You can see the option A, that is basically associative property of XOR. We know XOR, XNOR, both are associative. So I can say that option A, that is definitely true. Okay, let me tell you about some properties of XOR, XNOR, which will help you solving this question. You can see, maybe you already know, but this is a note, or I can say recap or revision. So let's see. We already know that an input XOR function is 1 if and only if odd number of inputs are 1. And remember, an input XNOR function is 1 if and only if even number of inputs are 0. Okay, these are very important results. The proof we have seen in our Go Classes lectures, but here only these results we need to understand and we need to apply these results. Okay, so these are very famous and very important results. So you can see an input XOR function, an input XOR operation is 1 if and only if odd number of inputs are 1. And an input XNOR operation is 1 if and only if even number of inputs are 0. So from these two results, we can easily prove these two results also. Basically, here you can see when n is even, means when the number of inputs is even, then n input XOR is complement of n input XNOR. So remember, when the number of inputs is even, then XOR is complement of XNOR. And when number of inputs is odd, then XOR is equal to XNOR. Okay, this is also very important. When the number of inputs is odd, then XOR, XNOR, these operations, these functions are same. And when number of inputs is even, then XOR, XNOR, these operations, these functions are complement of each other. Okay, very simple. So let's solve it here. You can see first option A. You already know that XOR is associative, XOR, XNOR, these are associative. So option A, that is definitely true. But can you prove it? See, either you can prove it with help of truth table, but we have 3 variables, so the truth table will contain total 8 rows. It will consume a lot of time. I taught you one method, that is by case method. You can apply the by case method and you can prove it. If someone asks you to prove the option A, means if someone tells you to prove the associative property of XOR, then how will you prove it? You can see what is option A, that is Q XOR R XOR S. This is LHS, that is equal to Q XOR R XOR S. So this is the option A. Now, can we prove it? I told you one method, a brilliant method, that is by case method. Okay, so let's prove it. Proof using by case. So let's apply the by case method here. You know that Q, R, S, these are Boolean variables. A Boolean variable is either 0 or 1. So remember, only two cases can be created. Either Q will be 0 or Q will be 1. Correct? Okay, either Q will be 0 or Q will be 1. There is no other possibility because these are Boolean variables. So they can take value either 0 or 1. So I can say that Q is 0 or Q is 1. Now you can see when Q is 0, then what this LHS will become and what this RHS will become. Let's see what this LHS will become when Q is 0. First of all, what is 0 XOR M? What is that? We already know that X XOR Y, that is equal to X bar Y or XY bar. Correct? So here you can see what will be 0 XOR M. So that will be 0 bar M or 0 M bar. Correct? 0 M bar, that is 0. 0 bar, that is 1. So here I will get M. Okay, so you can see that 0 XOR M, that is equal to M. So here when Q is 0, then we will get R here. Okay, we will get R and we have S. So you can see R XOR S. That is your LHS. What about RHS? Let's see. When Q is 0, then you can imagine this is M. Okay, so you can see 0 XOR M, that will be M. So I can say we will get R XOR S. Okay, so here you can notice they are same. Okay, but remember only in this case we have checked. So far we did not check what happens when Q is equal to 1. But I can say that when Q is equal to 0, then LHS, RHS, they are basically equal. And remember, Q is a Boolean variable. So either Q will be 0 or Q will be 1. And remember, when can I say two expressions are equal? Two expressions, two Boolean functions, two Boolean expressions are equal if and only if in all the cases they are equal. Okay, so if I can prove that when Q equal to 1, then also LHS and RHS are equal, then I can say that in all the cases LHS, RHS, they are equal. So I can say they are basically equal. Okay, so let's see when Q equal to 1. So here you can see what happens when I do 1 XOR M. So you can see that will be 1 bar M or 1 M bar. 1 bar, that is 0, 0 M, that will be 0. So here I will get M bar. Okay, so very simple, that 1 XOR M, that is M bar. Now let's see when Q is equal to 1, then what will be LHS, what will be RHS? So when Q is equal to 1, then here I will get R bar. Correct? Because you can see 1 XOR M, that is M bar. So here I can say when Q is equal to 1, then here I will get R bar and I have XOR S. And remember one thing, that this R bar XOR S, this is basically R XNOR S. Correct? Okay, so this we already know. This property you might already know, that R bar XOR S, that is equal to R XNOR S. Now let's see what about RHS when Q is equal to 1. So here you can see, you can assume that this is M. 1 XOR M, that will be M bar. Correct? So I can say what we will get bar here. What is the complement of XOR when you have even number of inputs? Here you can see we have two inputs. So even number of inputs, then XOR, XNOR, they are complement of each other. So you can see the complement of XOR here will be XNOR. So you can easily see that LHS, RHS, again they are same. So finally I can say that whether Q equal to 1 or Q equal to 0, in all the cases LHS, RHS are same. And remember, only two cases are possible, there is no other possibility. So I can say that LHS, RHS, they are always equal, so they are equal. So this is the proof of associative property of XOR. And you already know that XOR is associative, so I can say that option A you can tick. There is nothing else. Okay, now let's see option B, option C. There is something interesting here. In the option B, option C, they are using this word when. So if you remember, in the propositional logic we study what is the meaning of when. When means if. Okay, so you might already know this. You can see here we have this word when in the option B also, in the option C also. So you already know this from the propositional logic that when means if. You can replace when with if in the propositional logic, correct? Now here we have this type of sentence like x when y. Okay, so remember I can also write it x if y. I can also say that it is basically if y then x. Okay, because x if y. So you can see if y then x. What is if y then x? That is y implies x. Means when y is true, then what can you say about x? Okay, so remember when y is true, then x must be true. So remember when you see this sentence x when y, then how to prove this is true or false? This statement will be true when y is true, then x must be true. Okay, you assume that y is true, then x must be true. So very simple point. So remember one thing, that when you see this type of statement x when y, this statement simply means that if y is true, then x is true. You assume y is already true, then x must be true. If you can make x false when y is true, then I will say that this statement is false. Okay, I hope you understood. So let's see it here. What about option B? Option B is saying that here you can see this will happen when this will happen. Okay, so here remember we need to assume that this is already true. Then we need to check, is it always true or can we make it false? If we can make it false when this is true, then I will say that option B is false. I hope you understood this. Okay, so here please understand that the direction is not from here to here. The direction is from here to here. Okay, so now let's solve this. What option B is saying? Option B is saying that when, let's write like this, that when, let's start from here. Okay, when any two of the boolean variables q r s are 0 and the third variable is 1, then q xor r xor s will be 0. Yes, this statement is true. Why this statement is true? Because we already know that xor is 1. Sorry, this statement is actually false. This statement is false because XOR is 1 if and only if odd number of input variables are 1. Here you can see odd number of inputs are 1, then XOR will be 1. XOR will not be 0. So option B is actually false. I hope you understood. See, option B is basically saying that when this Q, R, S, two of them are 0 and one of them is 1. Okay, so let's take this. When Q, R, S, exactly one of them is 1. Exactly one of them is 1. Okay, now if exactly one of them is 1, then you can notice odd number of inputs are 1. Yes or no? If one of them is 1 and other two are 0, then odd number of inputs are 1, then XOR will be 1. Yes or no? Then in this situation, Q XOR R XOR S, this actually will be 1. Okay, so I can say that, this option B is false. I hope you understood. Okay, so remember option B is false. Very simple. Option A is already true, option B is false. Let's see option C. In the option C, we are saying when Q, R, S all are 1, then you can see odd number of input variables are 1 because all the three inputs are 1. So odd number of input variables are 1. Then XOR will be 1. Yes, XOR will be 1. So this option C is true. What about option D? Let's check option D. Remember, XOR is commutative as well as associative. So here you can see we have all the operators are basically XOR. You can see we don't have AND operation here. On the LHS, you can check we don't have AND operation. We only have XOR operation. And XOR is associative as well as commutative. So let's see this option D. Option D is saying Q XOR R, XOR R XOR S, then this whole thing then XOR, because remember there is no AND operation. All the operators, these are basically XOR operators. So XOR Q XOR X. Okay, this is equal to 1. What this will be equal to? Okay, let's check. Let's check. So here I told you that XOR is associative as well as commutative. Both, correct? Okay. So here what I can do, I can just remove all the parentheses, because remember XOR is already associative and commutative. You can just remove the parentheses because XOR is associative. Because of associative property, you can just remove the parentheses. So if I remove the parentheses, it will be like Q XOR R, XOR R, XOR S, XOR Q, XOR S. Okay, because of associative property, you can remove the parentheses. So I've removed all the parentheses. This is what I got. Now let's use the commutative property. When I use the commutative property, then this I can write as XOR Q. Or here you can notice one thing, that what is R XOR R? That will be 0. Correct? Because what is R XOR R? Here you can see both are same. And when both the inputs are same, then XOR will be 0. So R XOR R, this will be equal to 0. So here I can say that it is 0. And here I can apply the commutative property here. If I apply the commutative property, I can write it as XOR S XOR Q. And here remember, this S XOR S, this also will be 0 because they are same. So either both will be 0 or both will be 1. When both the inputs are same, then XOR will be 0. So here I got 0. Okay. So I can say that I got Q XOR 0, XOR 0, XOR Q. This is what I got. Now you can see 0 XOR 0, that is also 0. And what I can do, I can apply the commutative property and I can write it like this: Q XOR 0. Okay, correct? I can apply the commutative property. So here you can see that Q XOR Q, because XOR is associative and commutative. So here you can see that Q XOR Q, that will be 0 because these are same. Both will be 0, both will be 1. Okay, so I can say that XOR will be 0. Now finally I got 0 XOR 0 and 0 XOR 0, that is 0. So remember, this actually will be 0. And what option D is saying, that it is equal to 1, that is false. So the answer will be AC. For this question, the answer will be AC. Okay, I hope you understood. Is this clear to everyone? Is this question, is it clear? So let me just quickly see the chat. A student is saying, love you sir from Nepal. Thank you so much. It really means a lot. I'll pin your comment. So far everything is clear. Let me know. Thank you, Pradeep Kumar Yadav from Nepal. Thank you. Another comment from Tenabs. So thank you so much. Okay, so now let's move on to the next question. Very good. Sri Ram is saying, I got the same answer. Excellent. Sir, why using commutative property? We can use it. We can use associative property, commutative property. Remember, same question you can solve using multiple methods. I am just solving it, like this. You can see, I know that XOR is associative and commutative. So what I'm doing, because of associative property, I'm removing all the parentheses. I can remove all the parentheses and I can put parentheses anywhere because of associative property. This is the benefit of associative property. I told you in the group theory, in the Go classes group theory lecture in the discrete mathematics, I told you that because of associative property, you can remove the parentheses and you can put the parentheses anywhere. This is the benefit of associative property. And because of commutative property, I can switch them. Yes or no? This Q XOR S, I can write it as XOR Q. So because of commutative property, I can switch the operands of this operator. I can switch them. I can interchange them. And because of associative property, I can remove the parentheses and I can put the parentheses anywhere I want. So I am just taking the advantage of XOR being associative and commutative, and then you can see we are getting the answer. I hope you understood. And remember, XOR is 0 when both the inputs are same. So you can see R XOR R. Either when R is 1, then 1 XOR 1, that is 0. When R is 0, then 0 XOR 0, that is 0. Okay, so just these simple properties I am using and we are getting the answer. Very simple. Okay, so we have solved it. The answer is AC. Let's solve GATE Biomedical 2022 question. And this is another very nice question. The question is saying input bits X and Y. These are bits. X is a bit means X is 0 or 1. Y is a bit means Y is 0 or 1. So X, Y, these are bits. They are added by using the combinational logic as shown below. S represents the sum of the two bits. This represents sum of two bits. For a correct implementation of the sum, the signal D0, D1, D2, D3, what they will be. Okay, so first you understand that we are doing the addition of two bits X and Y. Okay, so let's see this. Actually, this is basically half adder. Yes or no? I told you that half adder is a combinational circuit which will do addition of two bits. So here you can see X is a bit. X is a bit means either it is 0 or it is 1. Y is a bit means it is either 0 or it is 1. This is given to you in the question. So you can see that we have X and Y, these are bits. This is the first thing to understand. Now let's see the second thing. The second thing is we are doing their addition. Okay, so let's do the addition. We will do X plus Y. When we do X plus Y, then you already know that there will be sum and there will be carry. Correct? Okay, there will be sum, there will be carry. That you already know. So when we do the addition. So here the two outputs are carry and sum. And remember the question is only interested in sum because you can see this S represents the sum of two bits. Okay, this is the sum output. This is the sum output of X plus Y. Of X plus Y. Okay, so first of all, you already know that this is a half adder circuit which will do the addition of two bits, correct? Full adder will do the addition of three bits and half adder will do the addition of two bits. So here, let's see what happens when we do 0 plus 0. When we do 0 plus 0, then sum is 0 and the carry is also 0, correct? And what happens when we do 0 plus 1? Then sum will be 1 and there is no carry, the carry will be 0. When we do 1 plus 0, sum will be 1 and there is no carry, I can say carry is 0. 1 plus 1, 1 plus 1. You think in the terms of decimal, then you can see 1 plus 1, that is basically 2 in decimal. So in the binary, it will be 1, 0 in the binary. Okay. So here you can see that this 0, this will be sum and this 1, this will be carry. So here I can say that sum will be 0 and there is a carry that is 1. Very simple. So here I can say that X, Y, we have two bits X and Y. So here you can see these are the possibilities. There are four possibilities here. 0, 0, 0, 1, 1, 0, 1, 1. What is sum? Let's call it S. S means sum. And let's see, C means carry. Okay, so you can easily notice here that when 0, 0, then sum and carry both are 0, 0. 0 plus 1, sum is 1, carry 0. 1 plus 0, sum is 1, carry 0. 1 plus 1, sum is 0, carry 1. Correct? Notice. Now here we are only interested in S. This question is only interested in this sum output. Okay, so let's write the sum output equation. So here remember we have got this truth table we have got from S point of view. We only care about S here. Okay, in this question. So here you can see 0, 0, 0, 1, 1, 0, 1, 1 and the S output that is basically 0, 1, 1, 0. Okay. Overall, now you can solve this question by two methods. Okay, so far we have done it. Now what you can do, you can just check, you can put the values and you can check. And there is another smart method also. Look at this circuit. In this circuit, what we have? We have these AND gates. Every AND gate has three inputs. And then we are doing their OR. So basically, just think about it that for this S, we are basically writing SOP expression. Yes or no? First, we are doing product. Product means we are getting the product terms. Then we are doing sum of product terms. So did you notice that? Did you notice that this circuit, this is basically AND OR circuit. First you have the level of AND gates, then there is OR gate. So this is AND OR circuit. And this AND OR circuit will give you sum of product expression. Sum of product, because we are basically doing sum of product terms. The output of every AND gate will be product term. We are doing sum of product terms. So you can see we are getting SOP expression. Here, what I can do, I can write the expression for S. If you remember, in the Go classes lectures, we have seen Shannon's theorem. On YouTube today, you search Shannon's theorem Go classes. Okay, just search it. Shannon's theorem Go classes on YouTube. Watch this lecture. I strongly recommend you to watch this lecture. Based on Shannon's theorem, there is one GATE CS PYQ also. In GATE 2006, a question came based on Shannon's theorem. Okay, on YouTube, you search this and you watch it. Now, after watching it, definitely you will definitely understand a lot of things. Okay, so let me tell you that when you have truth table, then how to write SOP expression? Very easy. You already know that to write the SOP expression, you will just see where the function value is 1. Okay, yes or no? So most of you, what you will do, most of you will write the SOP expression by considering where the function value is 1, and then you will just write the min terms for those input combinations where the function output is 1, and these min terms you will do the OR of these min terms and you will get SOP expression. So most of the students, what they will do, they will just consider these two rows because here the function output is 1, and now let's write the min term for these two input combinations and we can do their OR. So here the min term will be x bar y, or here the min term will be xy bar. Yes or no? Most of the students will do like this. Then you might be thinking, from where this D0, D1, D2, D3, from where these will come? Because here you can notice that here we are just getting two inputs. This is AND operation, two input AND operation, two input AND operation. But notice in this circuit, we have AND operation with three inputs. Every AND gate has three inputs. So from where these three inputs are coming? This you might be thinking. So actually, let me, or also remember, you might be thinking from where these four AND gates are coming. Here you can see that we are getting two AND gates. In this expression, we are getting only two AND gates. If you convert this expression to circuit, then what you will see? Then you will see that there are two AND gates and there will be one OR gate. Correct? This type of circuit you will get. Now you must ask yourself that from where four AND gates are coming. Here we have four AND gates. So from where they are coming? So let me tell you now. In this lecture also I have discussed Shannon's theorem Go classes lecture. You can watch on the YouTube. Now let me tell you that here you can write the expression like this: S equal to, what you do? For every input combination, you write the min term, and for that min term, what is the function output? You do the AND. Means what I'm saying? I'm saying that for this row, look at this complete row. For this row, I can say that x0, y0, and the output is 0. So here I can say that the min term is x bar, y bar, and here output is 0. Means for this min term, the output is 0. Okay, next, what is the min term for the next input combination? That is x bar, y. For this min term, the output is 1 plus x y bar. For this min term, the output is 1 plus, what is the min term here? X y. For this min term, the output is 0. Okay. So now can you notice what we got? We got four AND gates. Four AND gates we got. Did you understand? So now we got the four AND gates. Now what you can do? You can just solve it very easily. So the expression that we got, that is like this. Let me write it here. That S equal to this. S equal to, I got, you can see x bar, y bar, and 0. X bar, y, and 1, or x bar, y, x y bar, and 1, x y, and 0. Okay, so let me tell you here very simple point that you can see here. Now in this circuit you can notice, look at this AND gate. Here what are the inputs? What are the inputs to this AND gate? X bar, because there is inverter here. Okay, so don't forget about this inverter. Don't forget about this inverter. So you can see here what we have. Here we have, what is the output here? The output here is x bar y bar d d1, right? D1. So now you can just check x bar y bar d1. So I can say here this is your d1. This 0 is the d1. Okay, so d1 will be 0. Next you can notice, what about this AND gate? Here what is the output? Here the output is, you can see d3, and you can notice x x bar d3 and y. Okay, so x bar y d3. Okay, you can notice here, because here remember this y is going here, this here we are getting y. Okay, and here we are getting this middle input is x bar, and this is d3. So remember here, for this AND gate, the output is x bar y d3. So let's see, let's match here x bar y d3 with x bar y. This is d3, so d3 is 1. Okay, now let's see for this AND gate, what is the output? Let's see here for this AND gate. So the output here, you can notice that this y bar is one of the input. Okay, so y bar, you can see another input is x and another input is d0. So let's match here. You can see x bar, sorry, x y bar d0, x y bar d0. So remember this one is d0. And finally I can say that, look at this output of AND gate. So here we have x y d2. Okay, so you can see this is xy, so this 0 is d2. So what we got, the question is asking d0, d1, d2, d3 respectively. So d0 is 1, you can see d0 is 1, d1 d1 is 0. Okay, d1 is 0, d2 is 0, d3 is 1. Okay, so the answer will be 1 0 0 1. The answer will be option A. Now you might be thinking, we don't have to do this like this, right? There is another way. Okay, so let me tell you, very easy way. If you did not understand this, I hope you understand this, because this is a really beautiful idea. Here we are basically applying the Shannon's expansion theorem. Okay, that we have covered in our Go classes lectures. You can just watch it. But I hope you understood this method. But if you did not understand, I will just recommend that you watch this Shannon's theorem lecture. Once you watch it, I guarantee that you will understand. Okay, this method that we have seen, I guarantee you will understand this. Now there is another method, so let's see that also. Okay, just in case you did not understand this, then let me tell you there is another method. So let's see that method. You can see we have already seen that when x y are 0 0 0 1 1 0 1 1, then what is s, what is the output s? That is 0 1 1 0. Correct. Now let's just put in the circuit, in this circuit. Let's see, when x is 0, y is 0, then s must be 0. Okay, so let's put here, let's put x0, y0. Now you can notice this AND gate output will be 0, because this AND gate has one of the input y. Next you can see this AND gate has one of the input x. This x is going as one of the input to this AND gate. So here also output will be 0. For this AND gate, one of the input is y. Here also output will be 0. For this AND gate, both the inputs are x bar, y bar, and this d1. Correct. So you can see that here I will get, when x is 0, y is 0, then here I will get 1. Yes or no? Here I will, no, not 1 actually, I will get d1, because here you can see when x is 0, y is 0, then I have one of the input is d1, another input is 1, another input is 1. So it will be d1. Okay, and you can see what s will be. S will be equal to d1 or 0 or 0 or 0. That will be d1. And remember, when x and y are 0 0, then output must be 0. So this d1 must be 0. This d1 must be 0, means this d1, this must be 0. So I can eliminate option B, option D. These two options I can eliminate. I hope you understood. Very simple, right? Now let's see. When x is 0, y is 1, then the output actually should be 1. So let's check it. When x is 0, y is 1. Then you can see for this AND gate, the inputs are x, y, so the output here will be 0. For this AND gate, the inputs are y bar x. So here, because x is 0, so output here will be 0. For this AND gate, the input is x bar, another input is y. Actually, here you can see one of the input is y, another input is x bar, because x is 0, so x bar will be 1, and the third input is D3. So I can say that this AND gate output actually will be D3. Okay, D3. Correct? Because we already know D3 and 1 and 1. That actually will be D3. So you can see. And what about this AND gate? For this AND gate, the inputs are x bar, y bar. Because y is 1, so y bar will be 0. So here it will be 0. So you can see what is S. S will be equal to D3. And you can see when x is 0, y is 1, then S must be 1. S must be 1, so D3 must be 1. Correct? Okay. So you can see that D3 must be 1. So this D3, this must be 1. So which options? You can see we had option AC remaining. In the option AC, D3 is 1. Okay. So here I eliminated BD. But now remember, with this, I cannot eliminate between A or C. I cannot eliminate anything. Okay. So let's see quickly. Let's see where option A and C they are different. They are differing in D2. Okay. So also they are differing in, I think, yes, they are only differing in D2. Because they are differing in D2. So let's see where is D2. Here is D2. I know that option AC they differ in D2. Okay, so here we have D2. And you can see both the inputs are XY. So here the output actually is XY D2. Now let's see when XY are 1, 1, then what will happen? When X and Y both are 1, 1, you take X1, Y1. Now in this case, this AND gate output, that will become XY D2. So X and Y are 1, 1. So this will become D2. Okay, and the remaining AND gates, their output actually will become 0. You can check. You can check yourself. For the remaining AND gates, the output will become 0. So here, S will be equal to D2. And you can see S must be 0. Because when X and Y both are 1, 1, then you can see this S must be 0. So I can say that D2 must be 0. This D2 must be 0. So I can say this D2 must be 0. So I can say option A is correct. Okay, and I can eliminate option B, C, D. I hope you understood. So this is another way to solve this question. Is this clear to everyone? Both the methods, did you understand? In this question, all you have to do just remember that X is a bit, either it will be 0 or 1. Y is a bit, either it will be 0 or 1. And you just need to create this truth table for different combinations of X, Y. What will be the summation? The summation will be like this. Okay. Now you can just check. You can put XY 0, 0, and then you can see what is S. S must be 0. You can put XY 0, 1. Then remember, you can find S value. S value must be 1. You can put XY 1, 0. Then you can find the S value from the circuit, and that S value must be 1. Then you can put XY equal to 1, 1. Then from the circuit, you can find the S value, and that must be 0. So you can easily find D0, D1, D2, D3. Okay, very simple question. This is not a hard question, but the another method that we have seen, that is also very beautiful method. Okay, and I hope you understood from where these 4 AND gates are coming. Okay, I hope you understood. So you can see 4 AND gates are coming because you can write the expression for S in a different way. Okay, you don't have to consider only the rows where the function output is 1. Okay, most of the time we just consider the rows where function output is 1. But remember, there is another way to write the expression for S. What you can do, you can just consider all the rows. And what you do, you write every min term, and with that min term, you do the AND with the function value. It's like min term 0, and what is the function value? That is 0. Plus, min term 1 and what is the function value, that is 1, or min term 2 and what is the function value, that is 1, and min term 3 and what is the function value, that is 0. Okay, this is how you can write the expression for s. Okay, very simple. I hope you understood. So we have done the complete analysis of this question. So far everything is clear. From every question, from the complete analysis of every question, I hope you are learning something new, maybe some new approach, some new technique, something new. I hope you are learning. Okay, that is the purpose. When you keep learning something new, every day, then automatically one day you will become the topper. Let's solve GATE BM Biomedical 2022 question. And this is a brilliant question. This question we can solve using multiple methods. At least 3 methods are there. So let's solve this. In the circuit shown below, Y is a 2-bit output, Y1, Y0. So remember, Y1 is most significant bit and Y0 is least significant bit. So Y is a 2-bit output of the combinational logic. What is the maximum value of Y for any given digital inputs A1, A0, B1, B0? Now, this question you can solve either in the forward direction or in the backward direction. See what I'm saying. The question is asking that for any given digital inputs A1, A0, B1, B0, you already know that how many possibilities are there, how many input combinations are possible when you have 4 variables, 16, right? So you can see for A1, A0, B1, B0, total 16 input combinations are there. So you will have to check 16 input combinations, and then you will have to find what is the maximum value of Y is possible. So forward direction does not seem efficient, right? If you go in the forward direction, then for the input variables, there are 16 input combinations. For 16 input combinations, if you find the output Y value, Y is Y1, Y0, Y1 more significant and Y0 least significant. So for 16 input combination, if you find the Y value, then you find what is the maximum value, then that will consume a lot of time. The most efficient approach is you go backward. Okay, so let's see. I will solve this question using multiple methods. I will solve this question by writing the expression also. We can write the expression for Y0, we can write the expression for Y1, and then we can solve it. That is method. That is one of the method. That also we will see. Also remember, we will see the backward method. And that is the most efficient method for this question. So let's solve it. So let's see method number 1. In the method number 1, we will go backward. Backtrack. Let's do the backtrack. Here you can see the question is asking the maximum value of Y. What is Y? Y is Y1, Y0. Okay, so I can say that this is most significant, this is most significant bit, and this is the least significant bit of Y. Okay, very simple. So you can see this Y1, this is the most significant bit, this Y0, this is the least significant bit, and the question is asking for the maximum value of Y. Because Y is a 2-bit output, so what are the possibilities for Y? 0, 0, 0, 1, 1, 0, 1, 1. Okay, correct. Here something smart you can do. You can see these are the options. In the options you have 0, 0, 1, 0, 0, 1, 1, 1. Basically all the possibilities are there, because you can see Y is a 2-bit output, so only these are the possibilities. Now you can see all the possibilities are given to you in the options. Here you can play something smart. Don't focus on Y0, Y1 both. Just focus on Y1, because Y1 is the most significant bit. Now notice, if I can make Y1 equal to 1, then definitely the maximum value of Y will be either 1, 1 or 1, 0. Do you agree with me? The idea is very simple. See, the idea is like this. The idea is that if Y1 equal to 1 possible, if Y1 I can make 1, this Y1, only this Y1, if I can make it 1, if Y1 equal to 1 possible, then the maximum value of Y, will be either 1, 0 or 1, 1. So automatically you can see these two options will be eliminated. Okay, else if y1 equal to 1 not possible, if I cannot make y1 equal to 1, if that is not possible, then it means that y1 is 0. Yes or no? It means that y1 is 0. Then the maximum value of y possible, that will be either 0 0 or 0 1. Okay, this is the idea. I hope you understood. So let's see, can you make y1 equal to 1? That is the whole thing, because y1 is MSB and the question is asking for maximum value. So if I can make y1 equal to 1, then definitely answer will be either 1 1 or 1 0. If y1 is always 0, means y1 I cannot make 1, then answer will be 0 1 or 0 0. Understood? So let's see now, can I make y1 equal to 1? So try to make y1 equal to 1. Try to make this y1 equal to 1. Just try your best. You can notice this y1 is the output of AND gate. Correct? Here you have AND gate you have. So to make y1 equal to 1, I want to make y1 equal to 1. This is my desire, I can say. I want to make it. Okay. So to make it 1, because this is the output of AND gate, so you can see the output of AND gate is 1 when all the inputs are 1. Yes or no? So this input also should be 1. This input also should be 1. We are doing the backtrack. Correct? Yes or no? We are backtracking here. So you can see y1 equal to 1. Then definitely all the inputs of this AND gate should be 1. Correct? Okay, very good. Now I can say that basically this output of AND gate should be 1. And you can see the another input of this AND gate is output of this AND gate. So here also the output actually must be 1. Very simple. Because remember, for this AND gate, the two inputs are the output of these AND gates. So you can see the output of these AND gates, they also must be 1 1. Now you can see this is AND gate. This is also AND gate. The output of AND gate will be 1 if and only if all the inputs are 1. So here I can say that this also must be 1. This also must be 1. Correct? Similarly, for this AND gate, I can say that the output will be 1 if and only if all the inputs are 1. Means this input also should be 1. Also this input also should be 1. Very good so far. Now you can see that. You can see this input of this AND gate should be 1. It means that this output here must be 1. Okay, this must be 1. You can see for this AND gate, this input must be 1. So I can say that here this output is basically 1. But now something you notice that this is XOR. Here we have XOR gate. So for this XOR gate, the two inputs are 1 1. Yes or no? This is one of the input. This is another input. So you can see that two inputs are 1 1. If two inputs are 1 1, then what is the output of XOR? Output of two input XOR gate where both the inputs are 1 1, that will be 0. So there is a contradiction here. Did you notice? Because we want the output of this XOR gate also should be 1. So here you can see there is a contradiction. Correct? Clear contradiction you can notice here. So let me just write it here, that here you can see there is a contradiction. I hope you understood. Very simple. Remember, I am just saying that try to make y1 equal to 1. When you try to make y1 equal to 1, then remember here these AND gates are involved. Okay. For an AND gate, the output will be 1 if and only if all the inputs are 1. So here, if you just do the backtrack, then you can easily notice that the output of this OR gate, the output of this OR gate should be 1. But these outputs are input to this XOR gate. So you can see the XOR gate output will be 0, but we want it 1. For y1 to be 1, the XOR gate output should be 1. Yes or no? So here there is a contradiction. What it simply means? It means that y1 equal to 1, this is not possible. Y1 equal to 1, this is not possible. If y1 equal to 1 is not possible, then this option is eliminated eliminated, this option is eliminated. Means it simply means that y1 is definitely 0. Okay, so I can say that y1 is definitely 0. Whatever you do, y1 will be 0. Okay, now I can say if y1 is 0, then everything depends on y0. Okay, so you can see this y, this is equal to y1 y0, and you can see this y1 we have already seen, this is always 0. We cannot make it 1. So everything depends on y0. Correct? Now you notice the question is asking the maximum value of y. So now you see, can you make y0 1? Correct? Because now the answer will be either 0 0 or 0 1. So the question is asking for the maximum value of y. So among these two, 0 0 0 1, among these two, this 0 1 is maximum. So let's check, is it possible? Can I make y1 equal to, can I make y0 equal to 1? If I can make y0 equal to 1, then the answer will be option A. And if y0 also I cannot make 1, then answer will be option C. Okay, so here what you do, you try to make y0 1. Try to make y0 1. So let's see this y0. Let's try to make it 1. We already know, we have already seen that this y1 is 0. Anyway, we don't care about it. We just care about y0 now. Now you can see, let's see, can I make it? This is my desire to make y0 equal to 1, because the question is asking for maximum value of y. So if I can make y0 equal to 1, then the answer will be 0 1. Okay, otherwise the answer will be 0 0. So let's see, to make y0 equal to 1, you can see there is a XOR gate here. XOR gate output will be 1 if and only if, here this is a 2 input XOR gate. For 2 input XOR gate, output will be 1 if and only if both the inputs are different. Correct? Yes or no? So here I can say that both the inputs must be different, either 0 1 or 1 0. Okay, let me check both the possibilities. There is no problem. Correct? You can see this XOR gate, 2 input XOR gate, output is 1. So there are two possibilities. I can say possibility 1 and possibility 2. Possibility 1 is that this input is 1, this input is 0. There is another possibility, that is this input is 0, this input is 1. Okay, correct? So this is possibility 2. Let's check both the possibilities. First, let me check the possibility 1. Here you can see this input is 1. So it simply means this input is this, for this AND gate the output is 1. Notice, for this XOR gate, this second input is 0, and this second input is basically output of this AND gate. So here the output of AND gate should be 0. Okay, next you can see, for this AND gate the output is 1. So all the inputs must be 1. Here you must have 1, here you must have 1. Here you can see this line is 1. It simply means that here you have 1. Okay, next you can see this AND gate output is 0. What it means? It means that at least one of the inputs must be 0. Now notice one thing, for this AND gate the output is 1, so all the inputs must be 1. So here actually this input, both these inputs must be 1. And remember, this 1, this is the output of this XOR gate. So already we have seen that this is actually basically 1. And for this AND gate the output will be 0 if and only if at least one input is 0. But here you can see already this input is 1, so this input must be 0. Okay, do you agree? This input must be 0. Very simple. Now here you can see this line is 0, so it simply means here for this OR gate the output is 0. Okay, now let's see what about this XOR gate. You can see one of the input is 1, another input is 0. You can see this is one of the input here, and this is another input here. So you can see that for this XOR gate the inputs are 1 0. 1 XOR 0, that is 1. So there is no contradiction here. Yes or no? What we have seen, we can make y0 equal to 1. You can see, to make y0 equal to 1, all you have to do, at least one of a0 a1 should be 1. Here you can see that a0 or a1, if I make 1 and For this OR gate, the output should be 0. And OR gate output is 0 if and only if all the inputs are 0. And B0 is 0, B1 is 0. When you do this, then you will see that Y0 is 1. So remember, Y0 equal to 1 is possible. That's it. If Y0 equal to 1 is possible, then the maximum value of Y. So the maximum value of Y, that will be what? That will be 0, 1. Okay, is this clear? Because already you know Y1 is 0 and Y0 equal to 1 is possible. So the maximum value of Y, that is 0, 1. Here the answer will be option A. Okay, I hope you understood. So this is the method number 1. Here we are doing the backtrack. We are going in the backward direction. We are checking. First we are checking, can we make Y1 equal to 1? Then we see that, okay, Y1 equal to 1 is not possible. So Y1 is always 0. Then we are checking, can I make Y0 equal to 1? If I can make Y0 equal to 1, then answer will be 0, 1. Otherwise, the answer will be 0, 0. But here you can see that, yes, I can make Y0 equal to 1. Okay, I hope you understood. Now remember, I don't have to check the possibility 2. This possibility 1 we have checked, and Y0 equal to 1 is possible. This is all we want, that yes, Y0 equal to 1 is possible. So I don't have to check the possibility 2, because already we have seen that Y0 equal to 1 is possible in the possibility 1. So that's it. The maximum value possible for Y, that is 0, 1. I hope you understood this. Now let's see the method number 2. The method number 2 is forward direction. We can go in the forward direction. We can write the expression for Y0, we can write the expression for Y1, and then we can solve. Of course, I don't recommend this method, because you know, if I go in the forward direction, here we have XOR gate, here we have XOR gate, here we have OR gate, here we have AND gate. If I write the expression for Y0, if I write the expression for Y1, that will be complicated expression. Yes or no? Big expression will be there, complicated expression will be there. So I don't recommend this method, but anyway, let me just see. Let's see this method too. Maybe this also can give you some insights. Okay, so let's see this method. That is the forward method, forward direction. So let's see in the forward direction. You can see here, for this OR gate, the output is A0 or A1. For this OR gate, the output is B0 or B1. And you can see here, this XOR gate, the output, for a moment, let's assume that this A0 or A1, for a moment, let's assume this is M, so that I don't have to write it again and again. Okay, I just want to play smart. Okay, so here you can see this B0 or B1, let me write it N. So you can see, for this XOR gate, what is the output? That will be M XOR N. Now you can see this XOR gate output is input to these AND gates. So let me again assume that this whole thing, let me say that this is Z. Okay, I'm calling it Z, this whole thing, because I don't want to write it again and again. This M XOR N, I don't want to write it again and again. So let me write it Z. Now you can see what is the output here. Here the output is basically MZ, correct? And what about this output? Here this is NZ. So now you tell me, what is the Y0 expression? Y0 expression, here we have XOR gate. So basically you are doing MZ XOR NZ. And what is the Y1 expression? We are doing the AND gate. Here there is AND gate. So we are basically doing MZ and NZ. Okay, very simple. Now let's see what we got. So remember, first I am saying that A0 or A1, I am writing it M. B0 or B1, I am writing it N. Also, M XOR N, I am writing it Z. Okay. So finally, you can see what is Y0 and what is Y1. First, let me focus on Y1. Y1 is MZ, M and Z, and N and Z. Correct? Okay, yes or no? This is Y1. So here, Y1, that is MZ and NZ. So you already know that AND operation, that is associative commutative. So here basically I can say it is basically M and Z. Yes or no? Z and Z, that will be Z. Z and Z, that will be Z. So here I can say that you got M and Z. Now what is Z? M n, and you can see what is Z. Z is M XOR n. Correct. So here you can see what is M XOR n. Let's see. M XOR n, that is M bar n or M n bar. Right. So here now just apply the distributive property. So what we will get? Notice Mn and M bar n. Here because of this Mn bar it will be 0. Mn and Mn bar, here Nn bar it will be 0. 0 or 0 it will be 0. So you can see y1 will be 0. Did you notice? I am saying that Mn M bar n or Mn Mn bar. Here you can see because here mm bar, so it will be 0. Here nn bar, it will be 0. 0 or 0, so it will be 0. It will be 0. So finally I can say that y1 is 0. So y1 is always 0. This is what we have seen. If y1 is 0, then we can eliminate option D, option B. These are eliminated. Okay, simple. Very simple, right? So this method also, of course, it seems like a good method, but to be honest, the backtrack method was better. Okay. Here, let's see this y0. We have seen the y1. Now let's see the y0. So y0, that is mz XOR nz. Mz XOR nz. Okay. And remember one thing, that what is m? That is a0 or a1. What is n? That is b0 or b1. Correct. Here you can see m is a0 or a1, n is b0 or b1. And what is z? That is m XOR n. Okay. So here you can see what we got. We got mz. First, let's see this. What is this mz? It will be m, and this z I can write it. This z I can write it m bar n or mn bar. M bar n or mn bar. Okay, so we can write this. So here I can say that it will be m bar n or mn bar. This XOR XOR. Here you can see we have n z, n, and inside we have z. Z means basically m bar n or mn bar. Correct. Now let's see. Here you can see you just apply the distributive property. So this will become 0. Okay, this will become 0. So basically we will get here m n bar. This is what we will get XOR. And here you can see that this n with mn bar, it will be 0. So what we will get m bar n. This is what you got. Okay. Now here what? Here again you can open this XOR. So what it will become? Mn bar whole bar. Did we make any mistake? I think mn mz. Okay, so yeah, everything is fine, right? So you can see it will be what we will get. We will get mn bar whole bar m bar n. Okay, let me see. Just check it. Just do it. We are just opening this XOR. So you can see what we will get here. Mn bar whole bar, and this as it is mn bar and m bar n whole bar. Okay. So you can apply the De Morgan law. So it will be m bar or n, and here m bar n, or mn bar, or here m or n bar. You can apply the De Morgan law. Okay. So finally, what we are getting, you can see here it will be m bar n. Here also it will be m bar n. M bar n or m bar n, that is m bar n. Or here you can see mn bar and m, that is mn bar. Mn bar and n bar, that is mn bar. Mn bar or mn bar, that is mn bar. Okay. So this is what we got. Okay, something interesting, that we got y0 equal to, we got y0 equal to mn bar or m bar n. Okay, m bar n or mn bar. And what were mn? You can see m was a0 or a1, n was b0 or b1. Now you can notice one thing. Can I make y0 equal to 1? Can can we make can we make y0 equal to 1? So to make y0 equal to 1, what you will do? To make y0 equal to 1, you can see, because here we have XOR. So to make y0 equal to 1, both mn must be different. Yes or no? So both mn must be different. M and n, they must be different. Means I can say that I can make m0 and 1, or I can make m1 and 0, m1 and 0, right? Yes or no? Okay, so let's see. Can I make y0 equal to 1? To make y0 equal to 1, both mn must be different. So let's see, can I make m0 and n1? So yes, I can do that. Yes, possible. Yes, I can do that. You can see, I just want m0. To make m0, what I can do? To make m0, I will just make a1, a0 both 0. To make n1, I will just make b0 or b1 equal to 1. Means at least one of them 1. Yes or no? So very simple. I hope you understood. Okay, so remember, I can make m0 and 1. I can also make m1 and 0. This is also possible. Yes, possible. Yes, possible. Here you can see that to make m1, I will make a0 or a1 equal to 1. To make n0, I will make b0 0 and b1 0. Okay, so I hope you understood that y0 equal to 1 is possible. Okay, so that's it. I hope you understood. So finally, I can say the maximum value is the maximum value possible, that is 0 1. Okay. Now there is one interesting variation they can ask. They can ask you that the maximum value of y possible, that is 0 1. But for how many combinations? Can you tell me the answer for that question? Did you understand? I am asking a variation that for how many combinations? See, a variation. In the exam, they can ask you that this maximum value, this is possible for how many combinations? Possible for how many input combinations? Okay, this is a variation. Tell me the answer. I know that maximum value possible, that is 0 1. That is fine. Okay, the maximum value of y possible, that is 0 1. But for how many combinations? But for how many input combinations? This also they can ask. So for this variation, what will be the answer? You can easily see what we have seen so far. We have seen so far that to make y0 equal to 1, we already know that y1 is 0 always. This we have seen. And you can see to make y0 equal to 1, there are two possibilities. What are the possibilities? Either you make a1 or a0 equal to 1 and b1 or b0 equal to 0. Either you do this, or or you make A1 or A0 equal to 0. Here, this is B1. Okay, so B1 or B0 equal to 1. Correct? Yes or no? To make Y0 equal to 1. So here you can see how many combinations. Here both will be 0, but here three combinations are possible. At least one of them will be 1. So here three input combinations we got. Here three input combinations we got. Here also three input combinations we got. Okay, and remember one thing, that these input combinations and these input combinations, they are disjoint. They are disjoint, or I can say mutually exclusive. Okay, they are disjoint, or I can say mutually exclusive. Okay, let's use the word disjoint. This set of input combinations and this set of input combinations, these are basically disjoint. There is nothing common here. Okay, so the answer will be 6. So the final answer for this variation will be 6. Okay, that's it. So this is the complete analysis for this GATE Biomedical 2022 question. I hope you loved it. This type of question I think has not come in the GATE CS, but in the future they can ask, right? This is very much relevant to the GATE CS. This question you can solve either using backtrack or using the forward method. Which method did you like more? Let me know. We have seen two methods for this question. Which method has become your favorite for this question? Means for this particular question, which method did you like? Just share your opinion. Okay. So far, everything you understood? Let's move on. Let's solve GATE Biomedical 2020 question. Here you can see, match the Boolean expression with its minimum realization. So some Boolean expressions are given to us, and we need to match it with its minimum realization, means basically its minimum expression. Okay, minimize it and then match with the minimum expression. So this question actually you can solve either using K-map, but if you use K-map, then for these four functions, for these four expressions, you will have to create K-map. It might be time consuming. So what you can do, you can see some of them are actually very easy. You can just apply the algebraic simplification. You don't have to apply the K-map here, because if you apply the K-map, then for these four expressions you will make 4 K-map. It will be time consuming. So what you can do, just use the algebraic simplification. Okay, so let's see. Let me see the option. Let me see all of them one by one. With algebraic simplification, I will solve it. So let's see first P. So this expression P is saying x bar, y bar, z bar, or x bar, y, z bar, x bar, y, z bar, or x bar, y, z, x bar, y, z. Okay, so you can just apply the algebraic simplification here. You can see here we have x bar, y bar, z bar. Here we have x bar, y, z bar. So remember, x bar, z bar, they are same here. So you just take them out. Take them out. Okay, so you can take it out. X bar, z bar. Inside you will get y bar or y. That will be 1. Okay, so 1 or alpha or 1, that is alpha. So here I will get x bar, z bar, or x bar, y, z. Here you can see that we have x bar here, x bar here. You can take this x bar out. Then inside you will get z bar or y, z. Here you already remember, you already know this property, that alpha or alpha bar beta. Here you can remove this alpha bar and it will be alpha or beta. Correct? Okay, so here you can see that this is basically alpha. This z bar is alpha. So here we have alpha bar. So this alpha bar you can remove, and here you will get x bar, and inside you will get z bar or y. So let's see, x bar, z bar or y, x bar, z bar or y. So I can say that P is matching with L. You can see P is matching with L. So P is matching with K or not? No, P is not matching with K because in this K, we don't even have any complement. Okay, yes or no? So I can say that this option A eliminated. What about P matching with M? No, P is not matching with M. So this is also eliminated. So only two options are remaining now. Now let's see the next. Let's see Q. You can see XYZ or X Y bar Z or X Y Z bar. Correct. Now let's see here. You can just apply the algebraic simplification. Here you can see XZ. So you can take it out XZ. If I take this XZ out, inside you will get Y or Y bar, that will become 1. Okay. So here you can see you will get XZ or XYZ bar. Here you can see we have X here, X here. You can take X out. You will get Z or YZ bar. You already know this property that alpha or alpha bar beta is equal to alpha or beta. You can remove this alpha bar from here. So here actually this Z is the alpha. So this alpha bar means this Z bar you can remove. Okay, so you will get X and inside you will get Y or Z. So you can see Q is matching with X, Y or Z. Q is matching with X, Y or Z means Q is actually matching with K. Q matches with K. So you can see, does Q match with N? Does Q match with N? Q does not match with N, right? So Q matches with K. So you can see the answer will be option B. Answer will not be option C. Answer will be option B. Okay. Also, just take one more so that you are guaranteed to get a correct answer. So let's see this R also. We have got the answer, but let's see R as both. Okay. So let's see here. What about R? R is XY or XYZ. Here you can apply the absorption property or XYZ bar or X bar YZ. Now notice this XY here, this XY here, this XY here. You know the absorption property that alpha or alpha beta that will be equal to alpha. This absorption property you can apply here. So you can see this is alpha. Okay, so you can see that it will simply become XY and these will be gone. Okay, or X bar Y. So here you can take X, you can take Y out. Here you can take Y out. Inside you will get X or X bar, that will be 1. So finally I will get Y. So R equal to Y. R R is XY or XYZ, XYZ bar. So it will be XY or X bar, sorry, X bar YZ here. Okay, sorry. So I think some mistake I did. Okay, so here you can see X bar YZ. Okay, so here I will get XY or X bar YZ. Okay, so just a small mistake we did. So here you can see that this Y I can take it out. So if I take this Y out, inside I will get X or X bar Z. Here you can apply this property that alpha or alpha bar beta. You can remove this alpha bar and it will be alpha or beta. Here remember this X is alpha. So you can see inside I will get X or Z. So Y, X or Z. So R is matching with Y, X or Z. So R is matching with N. Okay, so remember R is matching with N because R is matching with N. So you can see only A or B can be correct answer. Okay, and already we have seen that that answer is option B. Okay, that actually we have already seen. So anyway, R is matching with N. Okay, let's see quickly this S also. In this S, let's quickly write it here. You can see we have, or maybe, okay, so let me write it here. Just quickly, let me do it. X bar, Y bar, Z or X bar, YZ or X, Y bar, Z or XYZ. So here you can see that we have here what I can do X bar Z, here also X bar Z. Okay, so I can take it out. So x bar z inside I will get y or y bar, that will be 1. Okay, or you can see here I have xz, here I have xz. So I can take it out xz, and inside I will get y or y bar, that will be 1. Here you can see I can take this z out. Okay, this z out. So inside I will get x or x bar, that will be 1. So that's it. You can see this s matches with z. Okay, so remember s matches with z. S will match with m. Okay, s will match with m, and you can see this r will match with n. So rs, they are matching with nm. Okay, rest we have already seen. The final answer will be option B. I hope you understood. Okay, so that's it. In this session we have solved total 5 questions from gate biomedical PYQs. Okay, these are digital logic questions related to K-map and Boolean algebra. I hope you enjoyed this session, and let me tell you that on YouTube you can search DPP Go classes, and you will find this playlist, this basically new series that we have started, that is for Gate CS GOAT DPP series. Okay, so just search on the YouTube DPP Go classes, and you will find the playlist also. You can notice one thing here. If you search it, then here you can see this is the complete playlist, Gate CSE GOAT DPP series playlist link. Okay, so this playlist you can bookmark, and in this playlist you will find question answer question answer question answer, like that. Every question will contain 5 questions. Okay, so question video answer video, question video answer video. Every question video has 5 questions. Okay, all these questions are taken from the standard resources. You can see in this session we have solved Gate Biomedical PYQs. In the next session we will solve from some other standard resources. Okay, so one more thing, that this series depends on your support. So if you like, comment, share. Okay, if you participate, then we will continue this series. This series we started almost 2 years back also, but because there was lack of support, lack of response from the students, so that is the reason, slowly it died down. Okay, so basically we tried to continue it, but there was very lack of response, very lack of support from the students. Now we have again started it. Now depending on your support, depending on your response, we will continue this. Okay, so just for your benefit, if you like a session, if you like a video, question video, answer video, anything, please like the session. Please share the word with all the GATE aspirants. This will be purely standard questions, nothing else. I will also tell you that, okay, this question is taken from this standard resource, so that you can also feel that you are solving top quality questions. All the GATE relevant questions we will solve. No question will be beyond the GATE level. All the questions that we will solve, these will be GATE level questions. Okay, I hope you enjoyed this session. In this session, for all the 5 questions, we have done the complete analysis. Some questions we have solved using multiple methods with proof, everything. Okay, so some variations also we have solved. So I hope you enjoyed this session, and we will continue this. Okay, so thank you everyone. Please share your feedback after this session is over. Okay, I can see in the chat students are putting the positive feedback. Okay, so if you have any doubt, please put in the comments. After this video is over, after this live session is over, in the comments you put your doubts. Any doubt, request, query, suggestion, any question, anything, just put in the comments. Okay, I will read your comments, I will reply to that. Okay, I'm very active on the YouTube, on the Go Classes YouTube channel. Okay, in the comments I will read and I will reply to it. Okay, so thank you everyone. Okay, please share the word with the GATE aspirants. Please share the question video, answer video. Let's see if they find it helpful, then they will also participate, and we will continue. Okay, thank you.